Hey everyone, welcome to today's Explainer. We are diving straight into a brilliant engineering detective story today, looking at one of the most complex faults in EV battery systems, the P0A03 pack voltage mismatch error. It's a severe system-level rationality fault, where basically the battery pack's total voltage completely refuses to match the sum of its individual cells. It's fascinating, so let's get right into it. Here's how we're breaking it down today. First, root cause analysis. Then, system architecture and fail-safes, moving on to DFMEA design prevention, then PFMEA production control, and finally wrapping up with DVPNR extreme validation. All right, Section 1, Fault Analysis.
So right off the bat, we're hit with what looks like an impossible physics problem. In a highly advanced precision-engineered battery system, why doesn't the total voltage equal the sum of its parts? I mean, why wouldn't the internal math actually add up?
Well, the conflict really comes down to a disagreement between two totally separate perception paths. On one hand, you've got the total pack voltage, or VPAC, and that's being measured by an independent high-voltage sensor. On the other hand, you have the sum of the individual cell voltages, which are accumulated by sequential AFE polling, and when a non-physical discrepancy pops up between these two pathways, boom, it triggers our main suspect, the P0A03 fault.
So what's actually causing this? The primary physical culprits are essentially invisible thieves, parasitic contact resistances hiding in your high-voltage bus bars, your contactors, and your fuses. Think about it. During extreme acceleration or heavy region braking, you have hundreds of amps surging through these nodes. Just a slightly loose bolt or a tiny bit of micro-oxidation creates milliohm-level resistance. And thanks to good old Ohm's law, that tiny resistance, when multiplied by those massive currents, creates a huge dynamic voltage drop. The independent sensor sees it, but the sequential AFE polling completely misses it.
But wait, there's an even trickier culprit here, and that's synchronization loss. AFE chips are polling those cell voltages sequentially, right? But the total voltage is being grabbed on a separate high-speed path. This creates this tiny 10 to 50 millisecond timestamp mismatch. It doesn't sound like much, but during a massive current surge, that millisecond mismatch acts like time travel. It generates a phantom voltage delta that literally tricks the software into registering a major critical fault. Moving right along to Section 2, Architecture and Failsafes. Now that we know what the illness is, how does the system actually protect itself? The BMS uses a pretty brilliant ASILD-level algorithm to fight back. First, a dynamic cross-check is constantly running the math on that voltage delta. Second, it uses a bus impedance model to actively estimate and compensate for that I times R voltage drop during high currents, which filters out those false alarms. But if a genuine hardware drift is actually detected, it triggers a fail-safe mode. This slashes torque to 50%, giving the driver a safe limp home mode to pull over without a sudden, terrifying loss of power.
All right, Section 3, DFMEA, Design Prevention.
Let's move upstream to the design phase. How do engineers architect the hardware to kill these risks at the source? It's all about the details. To stop sensor drift caused by condensation, they use Gore valves to seamlessly balance the internal and external pressure. Down on the PCB level, creepage distances and clearances are strictly enforced in the high-voltage zones to prevent surface leakage. They even integrate micro-fuses to stop short-circuit arcing in its tracks. Every single one of these design choices is about ruthlessly protecting that core measurement accuracy.
Which brings us to Section 4, PFMEA Process Control.
Because let's face it, theory's great, but it has to actually survive mass production. To ensure that, strict 5M1E controls hit the factory floor. To completely eliminate that busbar parasitic impedance we talked about, 100% of the connections are secured using robotic servo tightening. We're talking dual-parameter torque and angle monitoring locking in at exactly 9.0 Newton meters. After assembly, the PCBs go through an intense 3D AOI inspection, and then they get hit with a dense vacuum-conformal coating. This seals them off entirely to stop any moisture-induced electrochemical migration. And finally, Section 5, DVPNR Validation.
This is the climax, the validation torture chamber, where we prove the engineering actually holds up. In the hardware-in-the-loop tests, they intentionally induce poor contact, and then just blast the system with brutal 200-amp current steps. Under this extreme stress, the dynamic compensation algorithm has to keep the residual errors strictly within plus or minus 1.0 volt. That proves the software absolutely cannot be fooled by high current artifacts.
And how do they solve that annoying 10 to 50 millisecond mismatch we mentioned earlier? Simple. 1 microsecond. The system introduces a global hardware sync logic, so when the master controller broadcasts a command, every single AFE and total voltage chip must latch their voltages within exactly 1 microsecond. That completely wipes out those sequential polling delays.
Next up is the environmental torture. The boards get exposed to simulated coolant drips, and then they are locked in a double 85 chamber. That's 85 degrees Celsius and 95% relative humidity. Oh, and they are powered on for 500 continuous hours. The whole point is to aggressively accelerate aging and basically try to force a failure.
The make or break requirement here is that even after 500 hours of that high temp, high humidity nightmare, the insulation resistance has to rigidly stay above 500 megaohms. Absolutely zero metal dendrites are allowed to form. It's the ultimate proof that the conformal coating is completely flawless.
The last line of defense is end-of-line testing. By hitting the system with a massive step current pulse load, we can intercept micro-ohm level resistance defects with 100% accuracy. And they follow that up with a 2500-volt DC hip-hop test for 60 solid seconds. Leakage has to stay under 1 milliamp, which absolutely guarantees safety before that battery ever gets anywhere near a customer.
So we've unpacked the physics, the software, and the hardware of the P0A03 fault across all 5 dimensions. But it definitely leaves us with a provocative question for the future. If we can achieve this incredible 1 microsecond hardware synchronization, should we be integrating this sync logic directly with the contact or welding self-checks during the vehicle's ready phase? Honestly, where is the next frontier of vehicle safety going to take us? It's something to think about. Thanks for joining this explainer. I'll catch you next time.